Okay. So that stuff was basically the introduction stuff, and now we can start looking at it in context of Hess's law. So something to keep in mind with thermochemistry, like structure and bonding, you're going to get a question that is going to be your math-based question. It's going to be related to enthalpy. This question, I would say, kind of bridges on from the bond calculation questions that you did last year. It's very kind of therapeutic to work through. I personally really love Hess's law because it's like, so long as you know what you're doing and if you can work through the steps and you can double check your work, it's pretty idiot proof. And that then means that you should hopefully be able to catch your mistakes quickly. And if you get this calculation right, it's a very easy excellence point. So let me show you guys the process with it so that way you guys can find and make sure that you haven't made a mistake somewhere. So like I said, I really, really like this because it's idiot proof. So first off, we have to keep in mind something called Hess's law. So Hess's law is basically stating that I can get to the same answer in multiple ways. Either I have a single reaction or I have multiple reactions that the net result is going to result in the equation I'm looking for. So for example, this is an example of a chemical reaction, and I want to figure out the delta H of that. The R is just a term that we use for general reactions. Are we okay with that? So when I'm figuring out the enthalpy for this reaction, I could just use this reaction on its own. But if I don't have that information, I could also use the information from multiple equations and manipulate those equations together to get the same answer. So that is what Hess's law is stating. If I'm taking multiple steps or one step, I can still get the same calculation. The other way that I've seen it being defined, I'm just trying to find it in the book. It's giving you a lot of definitions for it. Cool. So Hess's law states that enthalpy change, heat involved or absorbed due to a chemical reaction is independent of the route pathway taken. So again, it also means that regardless of what reaction I use, if the sum of the reactants and products result in the same equation, then I can use my known bits of information to figure out an unknown. So that's the general concept. I'll show you guys how it works so that way you can actually see it. Because I feel like that's just a weird definition that doesn't make sense if you don't have any context. So in this reaction here, I'm looking at glucose being combusted. So you see how this is a combustion equation because I see glucose plus oxygen. The glucose is set to 1 mole. And when it does that process, it's forming carbon dioxide and water. I actually don't have the combustion value for that or the enthalpy change for that. So I need to now think about other equations to do that. Something to keep in mind when I'm looking at this is that the product for water is in the gas state. So I have to factor that into my steps. So I've been given a whole list of different chemical reactions, and I've been given the enthalpy for them. If I'm able to manipulate all these equations together, I can then figure out the unknown equation that I have up here. So I'm going to color code it so that way we can see what equation's doing what. So the first thing that I'm looking at is I have a formation. So these little letters are going to be becoming really important. The formation of sugar, and I have a value here. Now, something to keep in mind is that if I'm doing a formation equation, just find my notes from previous. Is it that one? This one, yes. So remember, with a formation equation, I'm taking the elements and I'm forming the product. So when I think about this equation here, the glucose is going to be on the product side, correct? Are we all okay with that statement? Glucose is on the product side based on this information here. I want it on the reactant side. So I need to flip it around the other way. So I'll do the equation first and then I'll flip it. So if I was to form glucose, I would need carbon plus hydrogen plus oxygen. These are 2's, and then I write that. C2H12O6. Are we okay with that? And then now I need to balance it. That should be a 6. That should be a 6. That should also be a 3. All right? 3, 3, 6. Are we okay with that? Now, I like to keep a list at the bottom to know how I'm manipulating my delta H. So right now, my delta H is a negative 1,270 kilojoules. I want to flip this equation around because I know this equation is not working as is. So I'm going to do that. So let's do another list. That way we can cancel it out. If I flip this equation around, again, I like to put all my arrows in the center. So that way everybody lines up nicely and I can cross them all out. So if I flip it around, I have C6H12O6. I have 6C. Okay? So this is just my sum. This is my original. All right? Now, since I've done this and I flip the equation around, I then need to change the sign. So this is now a positive. So let's do our totals. So right now from that first equation, my delta H from that is going to be a positive 1270 kilojoules per mole. Are we okay with that? All right, next one. How many equations we got? 1, 2, 3, 4. I'll do yellow. Okay. Ooh, actually, yeah, you got 4. Okay. Next equation here is the combustion of carbon. So that's going to be carbon with oxygen making carbon dioxide. So if I have my original equation, I would have C plus O2 equals CO2. Are we okay with that? All right. I look here at my reaction. My carbon dioxide and my carbon dioxide are both on the same side of the equation. So do I need to flip it? No, I leave it alone. What is something I need to fix though? That's a 6 and that is a 1. So I need to multiply this by 6 when I fix it. So let's go sum, fix, totals. So let's put that guy together. So I would have 6 carbons plus, if I multiply that by 6, 6O2 and 6CO2. Then for my totals, I would have my delta H in that case is going to be still the same sign, negative 394, but I need to multiply it by 6. So that value is negative 2,364 kilojoules per mole. Are we okay with that one? Yes or no? All right. Next one. Xander, you're giving me a face like you're not getting something.
The D is delta, it's only D is.
Where?
Well,
CR. This one?
the solid.
That one's solid. That one's solid. That one is talking about solid combustion. Yeah. So this is solid gas, gas, solid, solid gas, gas. Yeah. So that's fine. It's fine if it's solid. Combustion. This one?
Yeah.
The rule for combustion is, where'd you go? You are burning a substance in oxygen. So that's where I'm pulling it from. I'm assuming there's oxygen in the environment. All right, we'll do the last one. Oh, that was nice. They gave you the combustion of water or hydrogen. Okay, do that one next. Okay. Next one here is the combustion of hydrogen. They've given me that information. They've actually given me the equation already, which is very kind of them. They didn't need to. Again, look at this, look at that. Do I need to flip it? No, because the waters are on the right side. What do I need to do though? Multiply. So that's going to be multiplied by 6 as well, right? So since that equation is already there, I'm not going to rewrite it because I don't know why they gave you that one, but not the others. So I would have H2O. I need to be mindful. I know why, because they wanted to say this is the combustion. Sorry, this is the combustion if we form liquid water. That's an important note. So that's why they gave it to you. So liquid water. I'm just going to note the state for that one, which is a 6. You would have 6H2 plus 6 times a half is 3O2. So for my delta H then, calculations here, I would have negative 286 times 6. So 286 times 6. So you have negative 1761 kilojoules per mole. Well, I like to organize my things that way. Are we good? Okay. Last thing I need to think about is this bit here. So I notice that in this equation, My water is a gas. Very good, Xander, for watching out for all those states. Here, however, though, it is in the liquid form. So I need to make sure that my water is actually evaporating into the gas state, which is why they've given me the latent heat or the vaporization energy for the water. So if I want to go from liquid to gas, I need to have 601 kilojoules per mole. So all I would have in that case there is we have 6H2O as a liquid to make 6H2O as a gas. So delta H I'm adding in there is positive 601 times 6. So now I can add that to my total. So that's going to be 36. Okay. So what that is telling me basically is that if I make my water in the liquid form instead of the gas form, if I make my water in the gas form instead of the liquid form, I'm actually not going to have as much energy release because instead of the energy being released into the environment, it's gone to breaking the bonds. All right, now we tally this all together to make sure we have everybody, and then we can idiot check ourselves here. So I have 1270 minus 2364 minus 1716 plus 3606. So I have my delta H for the reaction, for the combustion of glucose, is negative 2773.94. We want three significant figures. So if I was to do that, it would be negative 2770 kilojoules per mole as my final answer. And then we idiot check ourselves. All right, you ready? Okay, let's idiot check. So I am looking, that's why I wanted to line up all my arrows to see if everything is canceling out. I can see that the liquid water is going to cancel out this liquid water, which is good. That's what I want because I want it in the gas state. I can see that this 6 hydrogen is canceling this 6 hydrogen. Boom, boom. I see that this 6 carbon is canceling out this 6 carbon. You guys can go away. Carbon dioxide I don't see on this side. And then the next thing I check for is my oxygens. 3 on this side, 6 on this side, only 3 on this side. So this 3 and this 3 get canceled, but I still have 6 remaining. And let's put everybody together because I don't have any waters on this side. So C6H12O6 plus 6O2. This is in the solid state. That's in the gas state. 6CO2 in the gas state, 6H2O in the gas state as well. Does this equation match what I have above? Yes. So you've idiot checked yourself. Isn't that nice? Isn't that therapeutic to work there? It's so beautiful. I like it. It's like if you have OCD, I feel like it's a very kind of like nice thing to work your way through because you're just like everything ticks and fits together. All right, let's see the marking schedule and then I'll talk about the last 2 bits here. All right, let me just pull up the marking schedule for you guys. I just love Hess's law. It's so therapeutic to work through. It's like the bond stuff. But the thing is with this one, you can actually check to make sure you got it right. Now, let's see if I actually it should be right. I don't see why it wouldn't be. Oh, I did not link my new lesson there. Oh, I didn't link it there either because I'm super smart today. I love math like this. It's so nice. Let me find it. There is the website. Okay. I didn't link it down here either. My goodness. Okay, level 3 chemistry exams. That tells me what I need to fix because I clearly was not thinking today. All right, we want thermochemistry. Where's the schedule? There it is. Okay. This is question, I want to say that was 3. Question 3C. Oh, interesting. They weren't picky. Okay. Here's level 3 chem. Here's all the working that we did. You see how it has that number here. In fact, they weren't actually stressing about the 3 significant figures. So long as you had it to between 2 and 4, they were going to accept it, which I was like, that's weird. Anyway, if you have correctly manipulated 2 of the equations or enthalpy changes, so for example, you multiplied by 6 or you changed the sign, that was enough for an achieved. So when I say that, flipping them around, or just recognizing you need to change the sign or multiply. If you did that for 2 out of the 4 equations there, you got an achieved point. The merit was a correct process with 1 error. So let's say you did a calculation error. That is why it's so important to show your work in this question. The last thing is excellence. Correct answer with unit, sign, and significant figures. So all the work that I have here is an excellence. That's it. All right. And like I said, the nice thing about this calculation is that it does idiot check itself. All right. Let me show you guys another version and then we are good to go. Okay. Here's another version of the same question. In this case, you do have a shortcut, which is quite nice. So let me show you how the shortcut works. So we are dealing with an equation with ammonia reacting with carbon dioxide. They have, weird, they give you so much. You should be able to use your shortcuts here. Yes. Yeah. Okay. Why did they give you all that? That's so confusing. Okay, never mind. Okay, this equation here, you can use a shortcut. And the reason why you can use the shortcut is because all the values they've given you here is in the formation setup. So all values are delta HF, and there has to be formation. You can use the shortcut. So shortcut works is delta RH is equal to the sum of, let me find the equation so I can actually write it nicely. On the next page. Next page. On the next page. Nope. Here we go. The sum of the formations of the products minus the sum of the formation of the reactants. Okay? So we're allowed a little shortcut here. So let's translate that into an equation. In this guy here, we're doing the formation of the urea. So formation of urea is going to be CONH2, like that. So I would need carbon plus oxygen plus nitrogen, plus hydrogen. So that is 2 and 2 is 4. So that's a 2, 1 carbon, half an oxygen, and then nitrogen is fine. All right, so that's the equation. I'm trying to think of ahead. I see why they gave you that delta. Okay, that's fine. Okay, ignore me. I know what I'm doing now. Sorry, I'm crossing that one off. Okay. So what I want to do is I want to think about this reaction here, and I want to think about everything that I've been given here. So I'm thinking about the sum, and I'm asking myself, what is product, what is reactant? So I see ammonia here, and I see ammonia here. Is that reactant or product? reactant. So that's a reactant. This one here, carbon dioxide, reactant or product? Reactant. This here, reactant or product? Product. All right, now we got to think about our numbers and our coefficients in front. This one here, what's the coefficient in front of the ammonia? 2. So we're going to multiply this by 2. The carbon dioxide, is there a coefficient in front? No. Water, is there a coefficient in front? No. All right, so what we're going to do is we're going to do this setup of the equation here. My delta HR is actually this number here, and we're trying to solve for this bit here. So let me set this up as an equation, and then we'll start plugging in our numbers. So I have delta RH is equal to the sum of my products. So I have the, for my products, I have delta FH of ammonia, and I have 2 of those. And the other thing in my, no, I lied. Let me start over. Products is on that side. Actually, let me move this out so we have more space. Delta RH is equal to my product. So one of my products is the water. What's the other product that I have? This one here. The formation of urea. Are we okay with that? So this is my sum of the products. Huh? I'm just showing you the setup of the equations. Then I'm subtracting away the reactant. So reactant-wise, I have delta FH of the ammonia. Now remember we have to times that by 2. And then the next thing we have to add in is our other reactant. So delta FH of CO2. And that's our reactants. I personally don't like this method as much because I find the other one easier. So if you want to use Hess's law for this, you can. You don't have to do it that way. Now I'm going to be substituting my numbers. So this number here comes from over here. This number here comes from over here. This number here is my unknown, so that is basically X. This number here comes from over here. And then what color have I not used? Orange. This number here comes from over here. All right, so let's plug in those numbers. It's awful, but we can get there. All right, negative 89 is equal to, close brackets, the water, which we're not multiplying it by anything. That is negative 394 plus X. So now it's just algebra at this point. Minus this value here. So the ammonia plus my carbon dioxide.
It's 94 twice.
Did I? I did. Oh, yeah, the first one is supposed to be water. Thank you. Good catch. Thank you. All right, then just plug it all in, solve for X. I'll keep doing the math, but I think you guys got it, hopefully. But you can see how easy, like, simple mistakes is going to add up. So that would be an example of why you get like a merit. Negative times a negative is a positive. I actually think this way's harder. I only printed enough. Sorry.
Sorry.
See ya. Hopefully that makes sense. Feel like I got the number wrong, but we'll see. X equals negative 305 kilojoules per mole. I actually don't like that method as well as the other one. I feel like this one's more complicated. Oof, the rain's coming down now. See if I got that right. I don't feel like I did. I feel like my number was a different number. Ooh, I did something wrong here. 244. 41. Oh, I wrote 81 instead of 89. I got the right number. There you go. Cool. And the thing is, if, yeah. Shouldn't be too bad. Okay. Recording stop.